Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 13-2, Seismic Design Seismic Force. In the previous lecture, we have considered 3 earthquake levels, and we have already talked about seismic forces corresponding to the 3 earthquake levels. They are design basis earthquake, maximum considered earthquake, small to moderate earthquake. And in this lecture, we will focus on design seismic force. In this lecture, we will determine the seismic force for the design of the structures. And here are some terminologies. Design seismic force, in Chinese, 设计地震力. Vertical distribution of design seismic force, in Chinese, 设计地震力之数项分配. Design seismic force is the total seismic force for the design of the structure, and it is distributed to every floors, every stories. After distribution, we have a story design seismic force, in Chinese, 楼层设计地震力. If we sum all the seismic force above the floor, then we can have story design seismic shear force, in Chinese, 楼层设计地震力. 楼层设计剪力, 楼层设计地震剪力. And in previous lectures, we have learned about seismic force corresponding to design basis earthquake, and also seismic force corresponding to maximum considered earthquake, and also seismic force corresponding to small to moderate earthquake. From these 3 seismic forces corresponding to 3 the earthquake levels, and we take the maximum one, and the maximum one will be the design seismic force. That's the seismic force for the design of the structure. We name it as VD, and VD equal to the maximum of V, design basis seismic force, VM, maximum considered seismic force, V star, small to moderate seismic force, and the maximum of these 3 seismic forces will be the design seismic force. It's the seismic force for the design of the structure. And this is design basis seismic force, and this one is maximum considered seismic force. And these 2 are small to moderate seismic forces. And this one corresponding to site class 1, 2, or 3, and this one corresponding to Taipei Basin. The seismic forces can be normalized in this way. V equal to I divided by 1.4 alpha y. If we move 1.4 alpha y to the left-hand side of the equation, and W also to the left-hand side of the equation, so that we can normalize the seismic forces, the seismic force corresponding to design basis earthquake, then we have the normalized seismic force equal to SAD divided by FU modification. Similar for maximum considered earthquake. And after normalization, then we can have 1.4 alpha y VM divided by IW equal to SAM divided by FUM modification. And also for small to moderate earthquake, the seismic force can be normalized in this way. For site class 1, 2, or 3, then we have 1.4 alpha y V star divided by IW equal to FU D star divided by 3 SAD star divided by FU star modification. For Taipei Basin, the normalized seismic force becomes FUD star divided by 2.5 times SAD star divided by FU star modification. And after normalization, we can compare these values, this value, and these values, and to find out the maximum and this will be the design seismic force. The maximum will govern the design seismic force, which is used for the design of the structures. And back to the example from previous lecture, we have V equal to 0.274 W equal to 40 ton force. That's the design basis seismic force. And the maximum considered seismic force Vm equal to 0.270 W equal to 39.4 ton force. And small to moderate seismic force V star equal to, there's something wrong here I think, equal to 26.8 ton force. And the question is to find the design seismic force Vd, and Vd equal to the maximum of design basis seismic force, maximum considered seismic force, and small to moderate seismic force. And then the maximum one will be the design basis seismic force. Therefore, Vd equal to 0.274 W equal to 40.0 ton force. Once we have the design seismic force, we would like to distribute all the seismic forces to the stories so that we can have vertical distribution of design seismic force. And design seismic force Vd is design based shear, which is distributed to every story. And after distribution is story design seismic force, FIF. FIF is the ith story design seismic force. And the summation of all story design seismic force equals design base shear of the structure, Vd. And Vd equal to summation I equal to 2, from I equal to 2 to NF plus 1, FIF. I equal to 2 is from the second story to the roof. That means that if we summation, we sum up all the seismic force from the second floor to the roof, then we will have the design base shear. That is the design seismic force, Vd. And story design seismic force, FIF, is proportional to story weight, WIF. Therefore, FIF is the story design seismic force of the ith floor is proportional to its weight, because inertial force is proportional to the weight, and seismic force is proportional to the inertial force, or seismic force is the inertial force. Therefore, FIF is proportional to WIF. And the structural vibration is always dominant by the first mode. Therefore, the higher the story, the larger the structural responses, including absolute acceleration. And inertial force is proportional to absolute acceleration, and seismic force is proportional to inertial force. Therefore, the story design seismic force, FIF, is proportional to the story elevation from the structural base, HIF. HIF is the elevation of the ith floor, ith story, from the structural base, from the ground. Therefore, FIF is the story design seismic force of the ith floor is proportional to its elevation. Well, now we have three conditions. The first one, the summation of all story design seismic force equal to design seismic force Vd, or design base shear Vd. And FIF, the story design seismic force is proportional to its weight. The design seismic force of IF is proportional to its elevation. And if structural vibration period T is shorter than 0.0 second, and the story design seismic force FIF can be written in this way. Therefore, according to seismic design code equation 2-18, then we can compute the story design seismic force of every floor. FIF equal to WIF HIF divided by summation J equal to 2 to NF plus 1 WJF times HJF times VD. Therefore, FIF is proportional to WIF. It satisfies this condition. FIF is also proportional to its elevation. It satisfies this condition. And summation of FIF from I equal to 2 to NF plus 1, then we can have the summation I equal to from I equal to 2 to NF plus 1 WIF HIF divided by the same numerator. Therefore, we can have the summation here equal to VD. Therefore, it satisfies these conditions. Therefore, the equation for the computation of the story design seismic force FIF satisfy all these three conditions. And here's the question for all of you. Fi plus 1F, is it always larger than FIF? That's the design seismic force of the floor above. Is it always larger than the floor itself? Therefore, the question is Fi plus 1F always larger than FIF? That's my question. And NF is the number of stories of the building. Okay, once we have the story design seismic force, and then if we sum up all the story seismic force, then we can have story design seismic shear force, VIF, is the summation of story design seismic force above. Therefore, VIF equal to summation from J equal to I plus 1 to NF plus 1 FJF. Therefore, the story design seismic shear force VIF equal to the summation of all the design seismic force of the stories above. And then if we consider the special case, first story design shear force, VIF equal to summation J equal to I plus 1 equal to I 1 plus 1 equal to 2. Therefore, the summation from J equal to 2 to NF plus 1 FJF. Then according to the relationship here, then we can have the design seismic force. Therefore, the first story, the design shear force of the first story equal to design seismic force or equal to design base shear. Design base shear here. And the question here for all of you is VI plus 1F always less than VIF. That is the design shear force for the I plus 1 floor. Is it always less than that for the I floor? Therefore, the design shear force above the floor, of the floor above, is it always less than the current floor? And here's an example. We take a two-story as an example. Then we can have F2F according to the equation here. F2F equal to W2F times H2F divided by W2F times H2F plus W3F H3F VD. And H2F is the elevation of the second floor. And H3F is the elevation of the roof. And W2F is the weight of the second story. And W3F is the weight of the roof. Similarly, for the story design seismic force for the roof equal to W3F times H3F divided by W2F H2F plus W3F H3F times VD. And in this case, we have H3F. The elevation of the roof is larger than H2F, the elevation of the second floor or the second story. And the question here is that if F3F always larger than F2F, that's my question for all of you. That is the story seismic force at the roof always larger than that at the second story? Once we have the story seismic force for the second floor and for the roof, then we can have the story design seismic shear force, VIF. V1F is the shear force at the first floor. Therefore, V1F equal to F2F, the seismic force at the second floor, plus this one should be F, F3F. That's the seismic force at the roof. The summation here, then it resulted in V1F equal to Vd. And for the second floor, the seismic shear force of the second floor equal to the seismic force at the roof. Therefore, V2F equal to F3F and equal to W3F, H3F divided by W2F, H2F plus W3F, H3F times Vd. And this is my question here, is V2F always less than V1F? The question is the story seismic shear force at the second floor always less than that at the first floor? That's my question for all of you. And then back to the example, and here's the information from our previous lectures. Then we have Vd equal to 40 ton, and the structural vibration period equal to 0.268 seconds. The weight of the second floor equal to 79.10 ton force. The weight of the roof equal to 66.95 ton force. And the elevation of the second floor equal to 3.0 meter. And the elevation of the roof equal to 6.0 meter. And the question is to find story design seismic force, FIF. Since T equal to 0.268 seconds is less than 0.7 seconds, therefore we can have the equation, the formula, to determine the story seismic force for the second floor, F2F equal to W2F, 79.10 times H2F equal to 3.0 meter, divided by W2F, H2F plus W3F, H3F times Vd. You come up with 14.85 ton force. Similarly, for F3F, that's the seismic force at the roof, design seismic force at the roof, equal to W3F, equal to 66.95 ton force, times H3F equal to 6 meter, divided by W2F, H2F plus W3F, H3F times Vd, and you come up with 25.15 ton force. And in this case, W3F, the weight of the roof is less than W2F, the weight of the second floor. And also the elevation of the roof, H3F, is larger than H2F, the elevation of the second floor. And finally, we have F3F, that's the design seismic force at the roof, is larger than the design seismic force at the second floor. Therefore, we have F3F larger than F2F. And then the summation of F2F, the design seismic force at the second floor, plus F3F, the design seismic force at the roof, equal to Vd. And we have this inequality in this case. Is it true for other cases? That's my question for all of you. And the next question is to find the story design seismic shear force, VIF. V1F is the design seismic shear force at the first floor, equal to F2F, the seismic force at the second floor, plus F3F, the seismic force at the roof, equal to 40.00 ton force. And V1F equal to Vd, equal to 40.0 ton force. And V2F is the seismic shear force at the second floor, equal to F3F, equal to the seismic force at the roof. From here, we can have F3F equal to 25.15 ton force. In this case, V2F is less than V1F, and V1F equal to Vd. Is it true for other cases? Is it always true? That's my question. So far we have considered the structural vibration period less than 0.7 seconds. And we have to consider other cases. If the fundamental vibration period is longer than 0.7 seconds, T is larger than 0.7 seconds, then extra seismic force Ft is applied at the roof. Ft is the force at the top of the building. When T is less than 0.7 seconds, there's no extra seismic force applied at the top of the building. When T lies between 0.7 seconds and 25/7 seconds, then Ft, the force applied at the top of the building, equal to 0.07 TVD. If T is larger than or equal to 25/7 seconds, then Ft, the force applied to the roof, is fixed to be 0.25 VD. The reason to have extra seismic force applied at the roof is that for mid to high-rise buildings, the first mode may not be a inverted triangle. It may be close to a parabola. Therefore, extra seismic force Ft is applied at the roof to simulate the first mode shape, the parabolic first mode shape. And this is taken from the Seismic Design Code equation 2-17. And in this general case, Ft is the story design seismic force FIF other than the roof. FIF is proportional to the weight of the floor, and also to the elevation is proportional to the elevation of the floor. Therefore, FIF equal to WIF times HIF divided by summation J from J equal to 2 to NF plus 1 WJF HJF, and then times VD minus Ft. And Ft is subtracted from the design seismic force Vd. And I equal to 2, 3 up to NF. For the roof, then we have the roof design seismic force F NF plus 1F. NF plus 1 is the roof, equal to W NF plus 1F times H NF plus 1F divided by the summation from J equal to 2 to NF plus 1 WJF HJF times VD minus Ft plus Ft. Extra seismic force is applied to the top of the building. And this equation is taken from the Seismic Design Code, equation 2-18. Then we have two questions here. The first question is Fi plus 1F always larger than FIF? That is, if the design seismic force at the I plus 1 floor is always larger than at the I floor. That means that the seismic force above the floor is always larger than the current floor. Another question is the summation of all the story design seismic force equal to VD. That's the summation from I equal to 2 to NF plus 1. FIF, is it always equal to VD? That's my second question. After having a story design seismic force, then we can have story design seismic shear force, VIF. And VIF equal to summation from J equal to I plus 1 to NF plus 1, FJF. Therefore, VIF equal to the summation of all the story seismic force above the floor. And we have two questions here. Is V1F equal to VD? That is, if the design seismic shear force at the first floor equal to design seismic force VD? That's my first question. The second question is VI plus 1F always less than VIF? Is the design seismic shear force of the floor above always less than the current floor? That's my second question. And here is a step-by-step procedure to determine design seismic force VD. The first one, step 1, from seismic design codes, equation 2-3, then we can have design basis seismic force corresponding to 475-year return period. V equal to I divided by 1.4 alpha Y times SAD divided by FU modification times W. That's the first step. And the second step, according to the seismic design code equation 2-16C, then we can have the maximum considered seismic force corresponding to 2,475-year return period, VM. VM equal to I divided by 1.4 alpha Y times SAM divided by FUM modification W. And in these two steps, we have design basis seismic force and maximum considered seismic force. And then we move to step 3. According to seismic design code equations 2-16A and B, then we can have small to moderate seismic force corresponding to 30-year return period, V star. And here's the equation for the computation of small to moderate seismic force as site class 1, 2, or 3. And here's the equation for Taipei Basin. After having design basis seismic force, maximum considered seismic force, and small to moderate seismic force, and the maximum one will be the design seismic force. That's the force for the design of the structure. And then we move to step 5 to find out the extra seismic force at the top of the building. According to seismic design code equation 2-17, then we have this equation. If the structural vibration period is less than 0.7 seconds, no extra seismic force is applied at the roof. If the structural vibration period lies between 0.7 seconds and 25/7 seconds, then we have extra seismic force, Ft equal to 0.07 T times Vd. And if the structural vibration period is larger than 25/7 seconds, then the extra seismic force applied at the top of the building, Ft, equal to 0.25 Vd. After having this extra seismic force applied at the top of the building, then we can compute the story design seismic force, FIF. According to seismic design code equation 2-18, the story design seismic force other than the roof, we can have this equation to compute the story design seismic force. For the roof, we have this equation to find out the roof design seismic force. NF plus 1, F is the roof of the building. Once we have the story design seismic force, then we can have the story design seismic shear force, VIF. VIF is the summation of all the story seismic force above the eye floor. Therefore, VIF equal to summation from J equal to I plus 1 to NF plus 1 FJF, and I equal to 1, 2 up to NF. And NF is the number of story of the building. And here's the reference for this course, for this lecture. The first one is the Seismic Design Course of Building, published in 2011 by the Ministry of Interior. And here's the video for Lecture 1, including English and Chinese version. Lecture 2, Lecture 3, Lecture 4, Lecture 5, Lecture 6, Lecture 7, Lecture 8, Lecture 9, Lecture 10, Lecture 11, Lecture 12, and Lecture 13. And this one is the current one, is under preparation. And you will be uploaded after this presentation. And from this lecture, we have studied about design seismic force VD. And design seismic force is the maximum of V corresponding to design basis seismic force, Vm corresponding to maximum considered seismic force, and V star corresponding to small to moderate seismic force. And the maximum of these three, then we can have VD, design seismic force, and we use VD for the design of the structures. After having the design seismic force of the structure, then we distribute all the forces to all the stories. Then we can have IF. IF is the design seismic force of the eye floor, and is proportional to the raise of the floor and also the elevation of the floor. Then we have the equation here other than the roof, and here is the equation for the determination of roof design seismic force. There's a design seismic force of the roof. Once we have the design seismic force of all the stories, then we can have design shear force, VIF. VIF is equal to the summation J from J equal to I plus 1 to NF plus 1 FJF, and I equal to 1, 2 up to NF. Therefore, the design shear force of the eye floor equal to the summation of all the seismic force of all the floor above the floor. And we have two questions for all of you. Is Fi plus 1F always larger than FIF? That is the seismic design force of the I plus 1 floor is always larger than that of the I floor? The second question is Vi plus 1F always less than VIF? Is the story seismic shear force of the I plus 1 floor always less than that of the I floor? That's the second question. That's all for this lecture. Thank you. See you next time. Bye-bye.